Here we have a right triangle formed by a real life situation where we have a bike path on one of the legs and we have a 200-yard walk on the other side of the leg, and then we have a walkway that is the hypotenuse of this right triangle. There's a lighthouse at one of the vertices, and the walkway is 400 yards long, and the angle theta is in the upper right corner of this right triangle. We're asked to find the acute angle theta, and acute means that the theta has to measure between 0 and 90 degrees between the bike path and the walkway. So we've drawn it so it's between those two. Okay, now we know that opposite side of theta is 200 yards. And we know that the hypotenuse side is 400 yards. So since we know, since we know those two sides and we don't know the other leg, B, the bike path, let's use the sine function. That makes the most sense. Sine of theta equals the opposite over the hypotenuse, 200 over 400, which simplifies to 1 over 2. Okay, so, if it's 1 over 2, I know a nice triangle that has a sine of theta 1 over 2. Okay, that's the situation I have. So which triangle do I know that has opposite over hypotenuse 1 over 2? Aha! That's my 30, 60, 90 triangle. There's my 90-degree angle, 1, 2, square root of 3. And down below on the lower left side, I have the 60-degree angle, and the upper angle is 30 degrees. So which one has the sine equal to 1 over 2? In other words, opposite side is 1, the hypotenuse is 2. That's going to be 30 degree, a 30-degree angle. See, I look at this picture that I have in the cloud, and I know the sine of that angle, 30 degrees, which is indeed at acute, is equal to opposite over hypotenuse 1 over 2. So that implies that the angle I'm looking for, the angle theta, in the picture of the walkway and the bike path, is 30 degrees.